Hey, we've got Ryan with us. Let's see who else we've got here. We've got Ashley and Ryan so far. Let me go get my cell phone in case I need it. I'll be right back, right after this. Well, let's see. Let's see who we've got here. Oh, we've got Stuart and Ryan, Ashley, and Nicholas. Good deal. Excellent. But it's just the five of us right now. I put my cell phone on the charger all night and it's only got 60%. Oh, gee. I guess I need to take it to the cell phone hospital. Modern technology, ain't it wonderful? All right, we got a good class though. Do you guys have any questions for me before we launch into our topic today, which is general motion of rigid bodies? But here's your chance to ask me a question. Okay, well, I guess you don't have any questions. So let me launch into the exciting world of general motion. Now there's three kinds of motion. I think I've told you this before, but there's three kinds of motion. There's well, let me ask you guys. Let's see if anybody listens to me. Let's see if anybody listens to me. Alex, unmute and say hello, please. Earth calling Alex. Earth calling Alex. Come in, Alex. Well,
rotation, translation, and combined.
That's it. Man, that's great. You guys listen to me. Now, that was Alex, right?
Yeah.
Yeah, I'm talking to Alex. There's there's pure rotation and I could write the equations for you. There's, I don't know, a handful of equations, 6 or 8 or 10 or 12 equations dealing with pure rotation. But I've written them for you before. They're in the flap of your book. And then there's pure translation. That's where you don't rotate. Your body can go in 3 dimensions in all kinds of zigzaggy, crazy ways, but it can't rotate. And then finally, there's combined motion. Some people call it general motion, but what it is, it's a combination of rotation and translation. Like if you throw a stick, go out to the river and throw a stick. Well, the stick will probably spin as it goes zinging through the air, and it has translation and rotation. It's got general motion. Okay, so now, thanks to Alex, we all know the 3 kinds of motion, and the topic today is general motion. Now, how do you go about solving general motion? Well, there's 3 methods for solving general motion. There's the absolute motion method, and that's explained in your book. Let me show you, see if I can find that here. Absolute motion method. Just a minute here. Absolute motion method. It's in your book on page 338. And then there's the relative motion method. And it is on page 346. And then the third method, these are all good. They all work perfectly good. It's just different ways of doing it. And then there's this one here. There's a third method called the, I'm too lazy to write it out. I call it the ICZV method, but it stands for the instantaneous. Is that how you spell instantaneous? No, I think that's an A. It's the instantaneous center of 0 velocity. It's the ICZV method. Now, of these 3 methods, I think this is the most difficult, the absolute method, but it has an advantage because you come up with an equation that you can program your calculator with. And once you figure out the equation, you can just plug in the number and push a button and get your answer. So that's nice. Now the relative motion method, it might be a little easier unless you're not happy with drawing angles and sort of a graphical. It's more of a graphical method. You have to draw some angles and some distances. But if you're happy with geometry type stuff and sines and cosines, it's a pretty good method. And then the easiest method of all is the ICZV method. Now, of course, the book presents this method here first, the hardest method, and then they present this one and then this one. Why don't we do it the other way? Why don't we start with the easy one? Doesn't that make sense? Let's do the easy method first, but I'll show you all three. So this one starts on page 360. In your book, the instantaneous center of zero velocity method. It starts on page 360. They have an example there of a bicycle wheel. Here, let me draw that. They've got a bicycle wheel, and what they've done is they've taken a photograph of that bicycle wheel while it's moving. It's moving. They put the shutter speed at maybe 1/250th of a second, or maybe 125th of a second. I really don't know, but you'll notice something if you stare at this picture here of this bicycle wheel. It's on page 360. You can see the spokes down here, but the ones up here are all blurry. How do you spell blurry? B-L-U-R-R-Y? Do you suppose that's how you spell blurry? Those of you that have books and are turned to page 360, you'll see what I'm talking about. You can see some of these spokes down here. Maybe you can make out one here and maybe one here. But you can't see these spokes here. You know why? Because those spokes are going faster. The instantaneous center of zero velocity is right here because the tire is on the road there, and it's not slipping or sliding. You're not laying any rubber. You don't have your brake on, and you're not moved. The tire is not moving with relative to the road there. And so these spokes here are not moving, but the spokes here are moving fast. If this is the ICZV, every point on that wheel is rotating about that point. It's not rotating about the center. See, that's where students get confused. They see that bicycle wheel and they say, oh, it's rotating about the center. No, it's not. Every point on this wheel, like you take this point right here, draw a line to it. That point is rotating, and it's got a velocity perpendicular to this position vector that I drew to the point there. This point here, draw a position vector to it, and then draw a perpendicular to it, and draw it a little longer because it's going faster than that. Draw one down here. This point right here, draw perpendicular, but it's not going very fast. See, I drew that velocity small. The fastest point on this bicycle wheel is way the heck up here. And I'll draw it longer. Because it's moving faster, it's blurry. You know, when you take your picture with your camera, to stop the motion, you have to have it on, well, at least 1/60th of a second. The center of rotation is not there. It's down here where there is no relative movement between the tire and the pavement. I hope that made sense. And now I'm going to show you how you find the instantaneous center of relative motion. We'll just do some examples here in a minute. There's a step-by-step method for finding the instantaneous center of zero velocity. Let me write it for you here. The first thing you do, there's 3 steps to find this. Okay, we already used 1, 2, 3. We're going to go A, B, C. Here we go. The first step is you get yourself a red pencil or pen, and you mark the velocities. Mark the velocities. And then the next step, well, you need to draw a perpendicular to those velocities. Mark some velocities on your body, then draw perpendiculars to those velocities. Now, where those perpendiculars cross, they'll cross someplace. That's the ICZV. That's how you do it. That probably didn't make a lick of sense, but we'll show you. We'll do one. But before I move on, is there any comment or question? You're awfully quiet. Okay, well, let's do one. Here we go. Now, we're doing the ICZV method first because it's the easiest. And then we'll move on to the others. Now, here's a problem here. Let's just do this one. This is on page 367. And it's problem P16.2. That P stands for preliminary, I think. This is P16.2b. It's in my book. It's on page 367. Well, they've got this long rod here, smooth pin, and then they have a kind of a connecting rod here and a piston. And the piston has to move on this flat surface. And they say that this long rod here is rotating. Okay, now there's 3 bodies here. There's the piston, there's this rotating rod, and then there's this connecting rod. This rotating rod is in pure rotation. It's rotating about this smooth point here. It's pure rotation. Let me write that. Pure rotation. In fact, it's going in a big circle. It's going in a great big circle, you know, it's going around that point that it's rotating about. And right here at this place right here, the velocity of that long rod is straight down. Now this piston here is pure translation. If you just tuned in and wondered, well, what's he doing now? I'm on page 367 in your book. This is preliminary problem 16.2b. And I'm writing the velocities. Now, the velocity of that piston, you've got to go just along the, call it the x-axis there. It's just going to slide along that surface. Okay, that's step 1. We've drawn, which is great. We drew. I'm going to go with we drew. We drew the velocities. Now what we're going to do is we're going to find where they cross. Make a line going through that velocity, make a line going through this velocity. Do you see where they cross? See, they cross right there. That point right there is the ICZV. It's the instantaneous center of zero velocity for this connecting rod. See, this connecting rod is in a general motion. G-E-N-E-R, there we go. It's in general motion. This rod here is in pure rotation. This piston's in pure translation. But this rod here, it's in general motion because what it's going to do, it's going to rotate counterclockwise a little bit. See, this point here is going to rotate down to here, and the connecting rod is rotating counterclockwise, and then this point on the connecting rod is moving to the right. This point here on the connecting rod is moving straight down at that instant. And I hope that made sense. Well, we just found the instantaneous center for that one. Let's do a different one. Okay, here we go. We're going to do a different one. Look on page 368. Any question on that one? All right, well, let's do another one then. Now this one's on 368, page 368. It's F1613, fundamental problem 1613, and what they have is they have a wall there. And they have, it's a 3, 4, 5 triangle kind of thing. They got a roller here. I need to make that a little bit longer. I'm doing it the wrong way. I'll get it here in a minute. Yeah, that's more like it. They have rollers on this rod here. It's a 5 meter, 4 meter, 3 meter rod. And this thing is sliding down. Let me get my red color here. They call this A. Well, here's the velocity of A. It's straight down. And here's B. And the velocity of B is straight over. And now what we're going to do is we're going to draw the perpendiculars to those velocities. Here's the perpendicular to that one. Here's the perpendicular to that one. And there's your instantaneous center of zero velocity. This rod is rotating at this instant about that point. Now, in this problem, they wanted you to calculate the angular velocity of the rod and the velocity of point C. Point C is here in the middle. We could go ahead and do that. That'd be fun. Now here's how you do that. The velocity of A is equal to R omega, where R is the distance here. That would be this distance here. Call it RA. That's a good name for it. It's 3 meters. Now, omega is the angular velocity of this rod. It is rotating. In fact, it's rotating like that. It's rotating counterclockwise. Okay. And this is equal to, let me read this. They said that this is 6. They gave us this. And they gave us this. Look here. This is 6 meters a second. That's given. This is 3 meters. That's given. So we can get the angular velocity of the rod. Well, I can do that. Time to show off a little bit. I'm getting the angular velocity of the rod. Why don't we give it a name? Omega AB. I'm getting 2 radians per second counterclockwise. Now let's write the same equation for B. The velocity of B is going to be the distance from the ICZV now, because that's where it's rotating. Do you understand? Every point on this rod is rotating about that point, times the omega of AB. Well, in this case, this is 4 meters. See, this thing here is 5 meters, but this distance is 4 meters. So you go 4 meters times, and we know what that is. It's 2 radians per second. So I can get the velocity of B. It's 8 meters a second. This velocity of B is 8 meters a second. Now they wanted something about the velocity of C. See, every point on this rod is rotating about this ICZV, and so is C. Now that distance there, that's 2.5. If you don't know why, I'll be glad to explain it. But it's 2.5 meters. And so the velocity of C will be 2.5 meters times the omega of AB, which we know it's 2. I can handle that. I'm getting 5 meters a second, but what's its direction? Well, this thing is rotating counterclockwise, so you have to draw perpendicular. This is not perpendicular. The perpendicular is kind of going like that. There's your velocity of C. It's 5 meters a second, but you'd have to draw perpendicular to this position vector from the center of instantaneous center. See this angle here. Well, you could figure those angles if you wanted to. You know that this angle here is 3687. You know that this angle here is 5313. And you know that this angle here is 5313 because you have a, what do they call that, isosceles triangle? And what's left over? I don't know, 5313 times 2, 106, and then you subtract from 180. This angle here, that angle there is 73.74 degrees. And if you really wanted, you could get this big angle here. It's bigger than 90. I'll tell you what it is. It's 106. That angle is 106 something. But if you make a 90, that's the direction of point C. Now let's look in the answer book and see how we did. This was F16.3. Go to the back. And we're going to look up F16.3. And they say the, am I getting mixed up here? What do they want us to find? F16. No, it's F16.13. I'm looking at the wrong one. F16.13. They said The velocity of c is 5 meters a second. Hey, that's what the answer book says. We did great. And they said something about theta is equal to blah, 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 36.9 degrees. Here's what they're saying. They're saying that this angle here is 36.9 degrees. Gee, I don't know if that's right or not. Beats me. I kind of got messed up because it's too messy for me to figure out. But I think we're okay on that. What do they mean 36.9 degrees? Any of you have any idea? I could figure it out. I don't want to. I got too much other things to do here. But I think that's how you do it. I've shown you how you found the instantaneous center. And now what we're going to do is we are going to do example, I think it's example 1612. I think that's what I want. Yeah. Okay, let's do that. Does anybody have any questions so far? That's kind of messy there, isn't it? Okay, well, here we go. We're going to do, this is example 1612. It's on page 366. Oh, come on now. Page, these things, come on. Page 366. It's example. I think these things dry up is what happens. Example 1612. Page 366. Let's draw these to scale, shall we? Now, you always do that, don't you? You always draw these things to scale. It looks like they've got a 45 degrees there. Okay. Well, let me do that. I'm going to try to draw this thing to scale. Now I need a 45 degrees, so let me get a 45 degrees here. Here's 45 degrees. Yeah. Right there. 45 degrees, okay, right? 30, 45, right there. Come on now, make a mark. Dang thing. You get a different pencil. Maybe this one will work better. We'll try. Okay, 45 degrees. Now, how long is it going to be? Well, it's supposed to be 25.25 feet. I wonder if we could go. Inches. I bet we could. Yeah. All right. I'm doing this to scale, guys. That's what you're supposed to do when you do your pictures. Come on now. Hey, oh, that one did good. Now what I want is 2.5. 2.5. That puts me right there. Perfect. 2.5. 2.5. Now this one here is 0.75 feet. So what I need for it is 7.5 inches. That puts me right That's me right there. Okay. More like that. Yeah, that's pretty good. See, I measured that. That's 0.75 feet, according to them. And this is 0.25 feet. Is that right? Yeah. Okay. And this angle here, we'll call it theta. And there's a piston right here. We'll put a piston right here. See? And we'll label all this stuff. This is AB. And this is C. All right. ABC. And to start with, we're going to do theta is 45 degrees. Okay. Great. Okay. Now, they said that this AB is in pure rotation. It's got pure rotation, and the angular velocity is 10 radians per second. It's going around and around in a circle. So AB is in pure rotation. AB is pure rotation. BC is this connecting rod. Wait a minute, let's talk about the piston. The piston at C is the piston at point C is in pure translation. It's going up in this case. The connecting rod BC is in combined motion. It has rotation, combined motion. Now, which way is the connecting rod rotating? Clockwise or counterclockwise? I'm going to ask one of my excellent students here. Jackson, unmute and say hello, please, Jackson.
Hello.
Hey, Jackson, that's a connecting rod, that BC. Is it rotating clockwise or counterclockwise? Jackson, you got a 50-50 chance of getting this right. What do you think?
Oh, I can see it. Would it be clockwise?
Stay away from the casino, Jackson. Stay away from the casino. This connecting rod, do you understand that this little guy here is going around in a circle? He's going around and around in a circle, around and around in a circle. And so the connecting rod, he's going like that. See, the piston's going up and the connecting rod is going in the circle. Here, I'll draw you. I'll show you what the connecting rod is doing. It's doing this. Do you see how the piston just goes up and down, up and down, up and I'll do that again. Up and down. Piston goes up, piston comes down. But right at this instant, the connecting rod is rotating counterclockwise. Jackson, can you see that?
Yeah, hold on. Okay, yeah.
Stay away from the casino, Jackson. It's going counterclockwise. It has an omega at that instant. It has an omega of BC, and we're gonna find what it is. And we're going to find the velocity of the piston while we're at it. But the very first thing we have to do is we have to find the ICZV. Okay, I'm going to shut up. And you need to have this scribbled down on your note paper. See if you can, excuse me. See if you can find where the ICZV is. I'll be quiet. Go ahead. Now to help you, some of you might have forgotten what to do. You've got to get a red pencil and you have to draw some velocities. Now B right at this moment is going, the velocity of B is going around in a circle. I just drew it. Now the velocity of the piston, it's going straight up. That's the velocity of the piston. That's the first step. You draw your velocities in red. What's the next step? What did I say? You draw perpendiculars. Here I'll write them again for you. Step number 1, you write velocities in red. Step number 2. Let me ask somebody. Let's see if you guys listen to me. Braxton, unmute and say hello, please, Braxton.
Hello.
Braxton, what's step number 2 in finding the ICZV? Step number 2.
Is it the perpendicular lines?
That's it. You draw perpendiculars. Perpendiculars to the velocities. Okay, well, let me do that. Hopefully you've already done this and you guys know where it is. Golly, I think I might go off the board here. I don't know, fellas, but perpendicular to that one puts you up here someplace. Oh, come on now. Now, perpendicular to this one, that puts you darn near made it. Hey, there it is right there, see? Kind of went off my board there, but right there is the ICZV. See, step number 3 is they cross someplace. Well, that's where they cross. That's where your perpendiculars cross. That's where the ICZV is. Now, the next step, I didn't tell you step 4, is you use this equation. Well, I used it here a little while ago. But to use it, we got to find these distances. I need some angles and some distances. Now, first, let's get this little bitty angle right here. They told us that theta was 45 degrees, didn't they? If you read the problem. If you just tuned in, we're doing example 1612. It's on page 366. They said this angle is 45 degrees. So what we're going to do is we're going to use the law of sines. And I know you know that by heart. We're going to go the sine of 45 degrees is to 0.75 feet as the sine of, we'll give this a name. How about alpha? Alpha is a nice name. The sine of alpha is to 0.25 feet. Okay, I'm going to shut up now for 45 seconds. And I want to know what alpha is. Go ahead and get it for me. Go ahead and get alpha for me, please. And I'll pick on one of my excellent students here. Ashley, unmute and say hi, please.
Hello.
What'd you get for that alpha, Ashley?
I got 13.6.
That's what I got. I got 13.63 degrees for that alpha. I don't know if we need this big angle down here, but we're going to get it. That big angle, I tell you what you can do. You can add 45 to this, and you'll get 58.63. Subtract that from 180. This big angle here is 121.37 degrees. See, you can use the law of sines again. You can go the sine of 121.37 degrees over AC. See, we can get the distance from A to C that way. We're getting all of our angles and all of our distances right now. I'm going to shut up again and give you half a minute. I want you guys to find AC, the distance from A to C. We're using the law of sines. Go for it. You can do this. Okay, I'm going to go to one of my superb students, Mark. Mark, unmute and say hello, please.
Hello?
Hello. Hey, Mark, did you get this distance from A to C yet?
I tried to.
What'd you come
I
up
got
with?
1.06.
That's not what I got. Do it again, Mark. Now, you might be right and I might be wrong, but that's not what I got. Let me do mine again. No, Mark, I didn't get what you got. Do it again. What'd you get this time?
I I don't know. I'm all over the place.
Well, we know alpha. We know everything. There's only one unknown in this equation. Did you take algebra in school, Mark? I'm teasing you. Never mind. I'm just teasing you. Of course you did. You can do that. Well, let me ask somebody else. Mark's stuck on that. Nicholas, what'd you get?
I got 0.91 meters.
Okay, now that's correct. But I want you to give me at least 3 digits on everything.
0.91 feet. I mean, oh, 99078.
Now, wait a minute, Mark. I'm getting 0.9056. I didn't get what you got. I got close. Do it again. Do it again. We got to get this right.
Yeah, I got 0.9056.
Good, good, good. Excellent. I need another on the 9056. Now that's feet, by the way.
Yeah.
Okay. Yeah, there we go. Now here's how you can check this. I did this thing to scale. I measured 2.5 inches for the 25 feet. I measured 7.5 inches. I don't know if you guys can see that, but I can. I can see it. I measured 7.5 inches for the 7.5 feet. Now this is supposed to be 0.9056 feet. So that would be about 9 inches if this thing is right. Well, let's see what it says. Well, boy, Jove, it's right on the money, 9 inches. See, when you make an accurate diagram, you can check it. One of my excellent students said it was 1 point blah, blah, blah. Remember? Well, that would have been 10 inches. Well, 10 inches is up here, guys. It doesn't check out. 10 inches doesn't check out. So if you make an accurate diagram, you can check your stuff. Now, if this is 45, and this is 0.9056, you know what this is? This is 0.9056. 9056 feet. Have you ever heard of an isosceles right triangle? That's what that is. It's a 45. This would be 45, you know it? It's a 45, 45, 90 triangle. So we have that distance. Now I need this distance here. Oops. I need the distance from the ICZV to point B. I'm going to shut up for a minute. I want you to find it. I need that distance, and then we'll be able to use this equation over and over and find out all sorts of fun things. Go for it. Find that distance. We could give it a name. We could call it IB. How's that? From the instantaneous center, I, to point B on the crankshaft. And I'm going to find it right now, and we'll see if we agree. Here we go. How about my friend Ryan? Ryan, unmute and say hi, please.
Hello.
Yeah.
Hey, Ryan, have you figured out this distance from I to B yet?
They won't quote.
Is it 1.176?
That's close, but that's not what I got. I got 1.03, maybe 1 if you rounded it off. Ryan, what you have to do is you have to get this distance from I to A, and then you have to subtract 0.25 from it. Is that what you did?
No, I didn't use the full triangle. I did the smaller one with the, but I see what you're saying.
You use this triangle here, Ryan?
Yes.
You can do that, but you'll have to figure out this angle here, which isn't too hard. Yeah, you could do that. But see, we don't know this distance here. Yeah, we do. We know, yeah, you would have to use maybe the law of sines to get it. Hey, did anybody else get 103? If you did, say uh-huh.
Yeah.
Yeah, I need another uh-huh.
Uh-huh.
There we go. See, what I did was I found the whole distance. It's a 45, 45, 90 triangle. I know you can figure the hypotenuse of a right triangle. I know you guys can do that. And then if you subtract that distance there, you'll get that distance. Okay, now we're ready. Now we're ready to find whatever we want to find. Like, for instance, the velocity of the piston. I think we want that. But first, we're going to start with the velocity of B. Well, the velocity of B, I need some room here. Let me make some room. Again, if you just tuned in, we're doing example 1612 on page 366. And I'm going to find the velocity of B. Well, the velocity of B is that just equal to the 0.25 feet times the 10 radians per second, which gives you 2.5 feet per second. And we know the angle, it's kind of going like that at an angle of 45 degrees. See it? So we got the velocity of B. Now the velocity of B can also be written as this 1.031 times the omega of BC. I use this equation over and over again. Every point on this connecting rod BC is rotating about this point. And so the velocity of B is equal to the distance, 1.013 times the omega of BC. And we know what this is. We just did it. It's 2.5. Okay. Now we're going to plug that in and get the angular velocity of your connecting rod. And we know which way that is. It's counterclockwise. Remember, we had that discussion earlier. This connecting rod is rotating counterclockwise at that instant. Okay. Find the angular velocity of the connecting rod BC. Here we go. Well, what I got was 2.425 radians per second counterclockwise at that instant. This connecting rod is rotating counterclockwise with this angular velocity. Now we can get the velocity of the piston. Every point on this connecting rod is rotating about this ICZB. So we can just take the 0.9056 feet and multiply by your omega of BC, which we just cooked up, and you can get the velocity of your piston. Go for it, get it. Well, I have the velocity of the piston. I'm getting 2.196 feet per second. Of course, it's going straight up. Now let's see if that agrees with their answer. They did this problem. And look down here at the bottom. Oh, they rounded off. Look, they got the same numbers we have. They took the 2.425 and they multiplied by 9056, just like we did. But they were just a little bit sloppy. They rounded it off to 2.20, which is okay. Feet per second for their answer. Hey, we got the book answer. Our answer is a little more accurate, actually, than the book. We just did that example 1612 using the ICZV method. Do you have any questions about it?
Yes, sir. I think I missed something. We're using the seconds to the -1 power. What's that for?
Well, that's radians per second. See, radians per second, remember radians are nothings. And so you
Right.
have nothings per second. So you can write it like that if you want. Now who am I talking to?
This is Taylor.
Taylor.
Okay, that makes sense.
You
Thank
okay
you.
on that?
Yes, sir.
Good question, though. Anybody else? Now, I told you guys there's 3 methods of solving these equations, or general motion problems. The ICZV is the easiest. Then there's the absolute motion method and the relative motion method. Let's do it those ways. Doesn't that sound like fun? We're going to do it the absolute motion method. Okay, well, let's see if I can show you how to do that. I need a little bit of room here. Need a little bit of room here. I hate to erase any extremely valuable information there. But here's my plan. We're going to make a little triangle down here. See that little triangle? And here's my plan. The distance from A to C is going to equal this little distance here plus that distance there. Well, this little distance here is 0.25 feet times the cosine of theta. You guys all know how to do sines and cosines and trigonometry. If this distance here from A to B is 0.25, then that little distance there, that's the adjacent. SOHCAHTOA. It's 0.25 cosine theta. So far, so good. Now this distance here, I'm going to write that. Let me save this. I might need this here in a little while. let me scoot it over here where I can grab it if I need it. I don't think I need it there. I need the room is my problem. And we got the V sub C there. Yeah, that gives me a little room. Now here's the plan. I'm going to add this distance here to it. That's going to give me the total distance from A to C. Okay. Now that distance there, let me think about this. I'm thinking, trying to figure out that distance. One way to get it would be to take the square root of 0.75 squared minus that distance there, which is 0.25 sine of theta squared. I told you this is the hardest method, and it's ugly. But you know Pythagoras. Pythagoras says this side squared plus this side squared gives you the 0.75 squared. We'll go back to Pythagoras. Well, this side here, you know what that is? That's 0.25 sine of theta. And then this side here, well, I don't know what to call it. We just call it delta y or something. But if you wanted to solve for that delta y, that distance from here to here, can you see that you take the 0.75 squared, subtract the 0.25 sine theta squared, take the square root by Jove, and you'd have it. That's that distance there. There's your distance from A to C. I hope I didn't lose you on that. I bet I didn't. You guys know Pythagorean theorem. Now, the reason why I did all that is, see, I want to find the velocity of your piston. And you know what that is? That's the derivative of this distance with respect to time. So we're just going to take the derivative of that. It'll be a little bit hairy, but we can do it. Now, the derivative of this is 0.25, I think it's negative sine theta, isn't it, calculus students? When you take the derivative of the cosine, it's the negative sign, isn't it? Somebody say, uh-huh.
Uh-huh.
Yeah. But you're not through yet because we're doing this with respect to time, not theta. So you have to multiply by d theta dt. It's called the chain rule. Right? So you're not doing the velocity of C is a distance. It's a distance of some kind. It's a y distance with respect to time, not theta. We're not taking derivatives with respect to theta. And so you have to use the chain rule. You know how that goes. You go d theta and then you go d theta dt. You got to have the chain rule. They call that the chain rule. Now here's the subtle part. That theta is getting smaller. As this crankshaft rotates, can you see that theta is getting smaller? It's not getting bigger, it's getting smaller, isn't it? So d theta dt, the way this book writes it, is just theta dot. It's not 10, it's negative 10. See, it's getting smaller. Theta is getting smaller. See, right now it's 45 degrees, but pretty soon it'll be 44 degrees, won't it? And then maybe 30 degrees. And then, well, as it spins, it gets smaller right at that moment. So we know what this is, it's minus 10. So let's put it in. Now you're multiplying, you're not subtracting, you're multiplying. Hey, but we're not done yet. We're trying to take the derivative of this ugly beast here. So far we've taken the derivative of this, but now we have to take the derivative of that. A little bit ugly. Well, you all know what this is. It's this quantity to the 1/2 power. In fact, here you could write it like that. Let's write it like that. That's the same thing, isn't it? Okay, so when you take the derivative of that, you get plus 1/2. Yeah, let me scoot this out of the way here. I might need it later, I don't know. When you take the derivative of this thing, you get 1/2 times the stuff inside. Well, that's just a constant. The derivative of that is 0. So if you want, you can put a 0 in there, but I don't need that stinking 0. Just forget it. And then you have a minus. There's a minus sign. And then you'll go 2 times 0.25. Oh, gee, I might run out of room, doggone it. To the 1 power. You guys all know how to do derivatives. You go 2 times that thing to the 1 power. Yeah. Then what? Well, then you have to take the derivative of this in here. It's called the chain rule. Now, the derivative of that in there is 0.25. Oh, I'm running out of space here. When you take the derivative of the sine, don't you get the cosine? Yeah. And you would be done if you were taking derivatives with respect to theta, but you're not. You're taking time derivatives. So you have to multiply by your theta dot, which happens to be minus 10. A little bit ugly. But I think we're done. I think we're done. I think we've got the velocity of our piston here. See it? It's not very pretty. Is that how you take the derivative? No, wait a minute. Auga. Auga. I think I forgot something. This is very ugly. When you take the derivative of this, you get 1/2 of all of this stuff. Wouldn't it be to the minus 1/2 power? Isn't that what you have to do? I think you do. I think you go 1/2 all of this stuff to the, and then you have to subtract when you get minus 1/2. No. Yeah, you do that, but then you have to take the derivative of the inside. And I forgot to do that, didn't I? I need a whole lot more room here. Let me do it up here. I need more room. I hope somebody took notes because I got to make some room here. How are we doing? We got 11 minutes. We might make it. I think this is correct. But what we're trying to do is we're trying to get the velocity of the piston. And what that is the derivative of this whole thing with respect to time. Now this I have no trouble with. That's 0.25. Well, it's a negative 0.25 sine of theta times theta dot, which I think is minus 10. You got 2 minuses there, they'll go bye-bye. And then here's where I fouled up. I think what you have to do is I think you have to go 1/2 times all of this stuff 0.75 squared minus 0.25 sine of theta squared to the minus 1/2. Well, that puts it in the denominator, doesn't it? Yeah, hey, why don't we just do that? Why don't we just put it in the denominator? What you'll have is all that to the minus 0.5. You'll have this here in the denominator. This doesn't scare us that bad, does it? See, you have all that. It was in the numerator to the minus 1/2, but that puts it in the denominator. And now you have to put in the numerator the derivative of the stuff inside. Well, I think I did that. I think that's all of this jazz. See, the derivative of that is 0, and then you have a minus 2 times 0.25 sine of theta times 0.25 cosine of theta times minus 10, which is theta dot. Yeah, I did that wrong, but I think I've got it correct now. I think we're looking at the velocity of c here. And it's a bit ugly, but I think we can do it. Hey, let me clean it up just a little bit. Hey, we're going to clean this up and make it pretty. Those two minuses make a plus. And if you multiply by 10, you'll get a positive 2.5 sine of theta. There's that term there. Now look at this. That's a minus and a minus. You know what? Those are two minuses. I think that makes a plus. And you see that 2 and that 1/2, that goes bye-bye. And so what you have is 0.25 times 0.25. There's a couple of those. See them? 0.25, 0.25. And you have, let me scoot that down just a tad here. And then you have sine theta, cosine theta. We took care of the minus 10 already, didn't we? Yeah. No, we didn't. No, we got rid of the 2's. And the minuses. But I think you're going to have to include the 10. And this term right here is divided by this. It's divided by 0.75 squared minus 0.25 sine of theta squared. I told you the ICZV method was a heck of a lot easier. All right, I'm gonna circle all this stuff. I think it's right. You see that ugly formula right there? I think that's it, by Jove. Now what I want you to do is I want you to plug in 45 degrees. Get your calculator. Can you guys read all that? I hope so. Get your calculator. Oh gosh, we only got 5 minutes. Get your calculator and plug in 45 degrees. Whoops, where's my theta? There's a theta right there. There we go. Plug in 45 degrees everywhere you see a theta and solve that. I'm going to solve it and see what I get. Here I go. Well, I did all that, and I tell you what I got. I got 2.197 feet per second. But see, I erased our answer. What is the correct answer? Does anybody know? Well, the book
Yeah, it's like
got
2.196.
yeah. Well, I have 6.5 right here, in fact. See what the book got was they rounded off to 2.20. You know what? That's correct. That is correct. Was anybody able to get, plugging in 45 degrees, was anybody able to get 2.1965? If so, say uh-huh.
Yeah.
Holy cow, that's two of us. Anybody else? I guess there's just the two of us. You see how ugly that is? But they call that the absolute motion method. Now, the beauty of it is this velocity of this piston is a function of theta alone. And your calculators, you have these $100 calculators. You can program that, and then you can put in your 45 degrees, and it'll give you an answer. Now, I've done that on my little calculator here. Let me see if I can plug that in. Now, I'm going to plug in 45 degrees. Okay. 45 degrees. If I can remember how to do this, which I don't. 45. And I'm going to plug it in. And then I push the button. And I'm getting 2.1965. Boy, Jim, what I've got is a 15C. You guys ever seen those before? It's ancient. I've had it for who knows, at least a decade. I plugged in 45 degrees. What I did was I put this equation in there, and then I can plug in any angle I want and get the answer. Isn't that nice? Well, we got 1 minute left in our class, and here's what I want you to do. Now, on the homework, it says you're supposed to do example 1612. But see, we've already done it for 45 degrees. Let's change the angle. Instead of using 45 degrees, use, I don't know, maybe 30 degrees. This is your homework. So when you draw your diagram, make that angle 30 degrees. See, that's 45 degrees. Draw it with 30 degrees. Do everything exactly like we did. Now, the beauty is this equation's still good. This equation's good for any angle. So you can, when you get through, you can check it and make sure you're right. If we had time, I would show you the relative motion method. And we'll do that next time. What is this, Wednesday? I'll show you that on Monday. But that's about it for today. Do you have any comments or questions? Anybody? Do you understand the homework? Your job is to do example 1612 on page 366, but change the angle to 30 degrees and keep everything else the same, but change the angle. I think it's slowing down. I think you're going to get an answer that's a little smaller because, see, it has to come to a stop. This piston comes up here, it stops, turns around and goes back. I think it's in the process of slowing down. Okay, nobody's asking me anything, so I'm going to say sayonara now. Unless, here's your last chance to say anything. Okay, bye-bye, students. I'll see you next time.
Bye.
Bye-bye.
But